One useful technique for integrating is called U-Substitution. And some students think that you don't really need to use this formally, but you'll see in a minute that it can be very, very helpful. Let's say we want to integrate the quantity x squared plus 3x, all raised to the fourth power, times the quantity 2x plus 3. Well, I guess one approach would be, let's just multiply everything out, and that's going to take you quite a while, but then you'll have a polynomial, and it'll be very easy to anti-differentiate. On the other hand, maybe we need to look at this as this is one quantity, and here's another quantity, and so I want to try and simplify this doing this technique called U-substitution. I'm going to take a temporary variable u and let that equal the most complicated portion of this integral, and that would be the x squared plus 3x quantity. Now, how did I know to set it equal to that? Experience. And the more you practice, and once we get through the end of this, you'll look back at the beginning of the problem and understand why I chose this. So it's usually looking a step or two ahead. All right, so I'm going to let u equal this stuff. So this is going to become u to the fourth power. But with this integral, everything is with respect to x. So what I'm going to need to do with this temporary variable is calculate du dx. And that's easy enough. That's 2x plus 3. But now if I multiply that dx to the other side, I have du is equal to the quantity 2x plus 3 times dx. Aha! Now you might see it. 2x plus 3 dx is exactly what I have here in my integral. So all of this stuff here, 2x plus 3 dx, I'm going to replace with a du. This quantity here I'm going to replace with a u, and then that'll be to the fourth power. So now this integral can be rewritten as the integral of u to the fourth power du. And that should be pretty easy for anybody to anti-differentiate. That's going to be 1/5 u to the fifth power plus any constant. Now, u was just a temporary variable. So once I finish anti-differentiating, let me go back and replace u, any u in my answer, with x squared plus 3x. So my final answer, switch to red, is going to be 1/5 times the quantity x squared plus 3x, all to the fifth power, plus any constant. And there you have it. Now, you may have been able to do this problem without this formal U-substitution. When you look at this, you realize, wait a minute, something to the fourth power, it's going to be 1/5 this to the fifth power. That's easy enough to figure out. But when you take the derivative of this, you multiply 5 times 1/5, that cancels. You lower that by 1, it becomes x squared plus 3x to the fourth, and then times the chain rule is going to be 2x plus 3, and that's where this came from. So seeing this 2x plus 3 as the derivative of this function here may have allowed you to come up with this answer right off the bat. But if not, this U-substitution is a nice technique to get that for you. All right, let's look at another one. How about this integral? The square root of x cubed plus 2x times the quantity 6x squared plus 4. Might be a good time to hit pause and try it yourself first. Okay, so if it's like the last problem, you think, well, the derivative of this is 12x, and I don't have 12x here. The derivative of this is 3x squared plus 2. That's not quite what I have here. So you may not be able to look at this and right away come up with the answer for the integral. On the other hand, let's try U-substitution. What should I let u equal? Well, if you notice, the more complicated part is going to be the square root of x cubed plus 2x. So I know that's what I want to focus on. So let's set u equal to what's inside the square root. Let's try that. X cubed plus 2x. Now let's take the derivative of u with respect to x. And that's going to be 3x squared plus 2. and we look and say, well, we can move the dx over here, but that's not quite what I have here. Although it's almost exactly what I have there. So du is equal to the quantity 3x squared plus 2 times dx. Now, how does that differ from what I'm dealing with in my integral? Well, it only differs by a factor of 2. If I multiplied 3x squared plus 2 times 2, I would get 6x squared plus 4. So let me do that. Let me multiply both sides of this equation by 2. And now I'm going to have 2 times du. I'll distribute that 2, so it becomes 6x squared plus 4 times dx. Now that's exactly what I have here. So I can replace this 6x squared plus 4 dx with 2 du. And this part I can replace as the square root of just u. So let's write that new integral in terms of u. So we have the square root of u, or u to the 1/2 power, and then times 2 du. So if you like, you can move the constant term out in front of the integral. We can write this as u to the 1/2 power. So what's the antiderivative of u to the 1/2 power? Well, if I add 1 to the exponent, it becomes u to the 3/2 power. I need to offset that with 2/3. So when I take the derivative, I get a coefficient of 1. And don't forget the constant 2 we had out in front. And then plus any constant c. So final answer here, I've got 4/3 u to the 3/2 plus a constant. Now, that's in terms of u. That was just a temporary variable. So now I can go ahead and replace u with x cubed plus 2x. And I'll have my final answer. So we get 4/3 times the quantity x cubed plus 2x, all raised to the 3/2 power, plus c. And the nice thing about doing integrals is you can always differentiate your answer to make sure that that's the integrand that you started with. So if I did take the derivative of this, I'd do 3/2 times 4/3. Well, let's actually go ahead and write this out to show you that it works. So the derivative is going to be 3/2 times 4/3, and then the power is going to be lowered by 1, so 3/2 minus 1 is 1/2. And then we have the chain rule times the derivative of the inside, which is going to be 3x squared plus 2. I need to put that in parentheses. So these 3's cancel. 2 goes into 2 once, 2 goes into 4 twice. And so I'm left with 2 times that quantity. And if I distribute this 2 into the second parentheses here, I'll have exactly what I started with. So we're good. Let's go ahead and move all that out of the way. And there's your final answer. Let's try one more example. See if you catch on to this. Once again, maybe you want to try this on your own first. So hit pause, give it a shot, and then come back and see how I work through it. Okay, we want to find the integral of tangent of x. So that doesn't seem like U-substitution is going to do us any good. I mean, you might just say, oh, so am I supposed to let u equal tangent of x? Well, then when I differentiate du dx, what's the derivative of tangent? That's secant squared. So if I multiply the dx to the other side, I get secant squared x dx. I certainly don't have that in my integrand here. I have the tangent, but I don't have a secant squared. So you might think, well, what if I divide both sides by secant squared? Oops, of x. But see, now that's in terms of x. So, and I could write that as cosine squared of x times du. And you can see the trouble we're going to have here. So I can rewrite this integral. The tangent of x just becomes u. The dx becomes cosine squared of x du, and I'm even worse off than I started. So sometimes you have to actually go down the wrong path to get better at doing U-substitution or integrals in general. So that doesn't seem like that's going to help us. So what else can I do? Well, maybe I could rewrite the integral in a different form. Well, we know tangent is sine over cosine. So let's try that. Now what should I let u equal? Well, you might think, how about let u equal sine of x? Let's see what happens here. Take the derivative with respect to x, and you're going to get cosine of x. And then multiply the dx to the other side, and I'll get cosine of x dx. And I do have a cosine of x in my integral. I do have a dx, but it's the cosine x is in the denominator. It's not in the numerator, so this isn't going to work. It's not going to help me out. So once again, that only leaves one option. What if we let u equal the cosine of x? Let's see what happens here. The derivative of u with respect to x is negative sine x. The negative isn't really a problem. And if I multiply both sides by negative and dx, I'm going to get negative du equals sine of x times dx. And sure enough, sine of x dx I've got in my original problem. So that sine x dx I can replace with negative du. And this cosine of x in the denominator I can replace as 1 over u. So now we can rewrite this, and we have the integral of 1 over u that covers our cosine of x. And then the negative, I'll put the negative outside here, du. And that looks like something we can handle. So you might want to write that as u to the negative first and see what happens there, and try and do a power rule, reverse power rule. But then you're going to realize that that's not going to work, and the derivative of 1 over u is the natural log, the absolute value of u, plus any constant. So now I'm ready to go ahead and replace what u was equal to. U was equal to cosine of x, so I'll plug that in there. And I get negative natural log, absolute value, cosine of x, plus any constant. And that's my antiderivative of tangent. Let's check. Let's take the derivative. The derivative of natural log of something is 1 over something. And then times chain rule, the derivative of that something, derivative of cosine, is negative sine. The negatives cancel each other out. I have sine over cosine, which is tangent. Voila. Magic. Math magic. Okay, so hopefully this gives you a little better understanding of U-substitution. And like I keep saying, the best way to get really good at integration is by practice. And the more you practice, the more you'll start to see some of these problems 1 or 2 or 3 steps ahead, and you won't have to make so many mistakes and then try back from the beginning. The assignment problems are on 16E, page 395.